now. So last time we arrived to define the equation that governs, in the case of overdamped limit, the time evolution of the probability density defined by stochastic processes obeying the overlapped Langevin equation. So basically what this equation is telling me is that, for instance, suppose you have, just as an example, suppose I have a bunch of Brownian particles that are sufficiently dilute that they don't interact with each other. They only interact with an external potential U in 1D. This is just an example. Suppose I put them all in say, in the same positions, for example, here, or here, or any other places. Of course, this position will evolve with time. And if you think about it in terms of just heuristically, in terms of your physical intuition, what you will imagine that after a while, they will spread. After some later time, they will sort of fill up this room. But then occasionally, some of these particles by Brownian motion will venture to the top of the mountain because of rare fluctuations in which they get kicked a sufficient amount of time in the same direction. And they will begin to populate the other side. And eventually, if the system approaches equilibrium, which is something we will need to discuss a bit further later today, then ultimately the system will evolve to configurations in which you have equilibrium. And if the system approaches equilibrium, then I expect that P of x of t will converge to the Boltzmann distribution as a function of position in the large time limit. Do we agree? So this is the physical meaning. And if we are right, then we must be able to see how this is coming directly from this mathematical equation. Now, remember, in the Fokker-Planck equation is a mathematical consequence of the Langevin equation. And the Langevin equation was derived starting from the Hamiltonian. And there was one particular relationship that we discovered that came directly from integrating the Langevin equation. And it's the following. The first is that the noise in the Langevin equation, well, let me rewrite the Langevin equation here. I'm going to write it for one dimension for simplicity. You can write it for multiple dimensions. So the noise has zero average. And since it's a Gaussian noise, I need only to specify its first moment. And we emphasize that this number, the variance, if you want, the variance of my noise was actually a number that was mixing the two fundamental parameters of the Langevin equation. Remember, Langevin equation incorporates all the ultraviolet physics associated with the fast motion of the environment into effective theory parameters, just as much as the coupling constants in the hardcore potential in the Schrödinger problem, right? And there are only two parameters because we are assuming memoryless kernel. delta function kernel. If you had more terms in the delta expansion, we would have had more parameters, right? In the simplest descriptions, we have only one parameter. So we have one parameter associated with dissipation, but we also, this parameter gamma is the dissipation rate, also called the collision rate, because its physical interpretation is how often you collide or interact with environment, right? But there's also one other parameter that is associated with fluctuations. Who tells me what the other parameter is? Physical parameter. What is the other physical parameter in my calculation that is not there in the Hamiltonian formulation that enters after I do my averages and has to do with fluctuation? I mean, it's the usual suspect, so it shouldn't be hard for you to guess.
Temperature.
Temperature, KT. Now, if you perform the calculation in the way we performed, we discover that this correlation function depends on a constant d called the diffusion coefficient that is a specific combination of gamma and KT. So there is a specific ratio. So the noise in my Langevin equation is not just an arbitrary parameter. Because if this parameter was arbitrary, then I would not be able to gauge how much energy is flowing in and how much energy is flowing out. Since I'm coupling my system to an environment and I'm keeping track of the energy flow because I'm doing Hamiltonian dynamics, the theory knows about the energy flows from the system to the environment and from the environment to the system. And as a result of that, after I do my averages, it returns to me a specific relationship between a specific combination of fluctuation dissipation that is the result of this very careful balance of energy, outflow and inflow. And this is called the diffusion coefficient. And the fact that the diffusion coefficient is a combination of collision or dissipation rate and temperature, in this specific combination, and for instance, say not another one, it's difficult to cook up another one with the right dimension, but you know, this is called the fluctuation dissipation theorem. Okay? Now, this is a fundamental result because it's telling me, now, when you do statistical mechanics, you have your nice ensemble formulation, but do you ever show that you achieve thermal equilibrium? Demonstrate mathematically. Think about it. You actually never solve dynamical equations showing that they lead to equilibrium. You have your nice formulation, and then you say, at equilibrium, the phase space distribution must be constant by definition. It's part of the ergodic assumption, if you want. And this is simply because there is no dynamics in the Gibbs theory of ensembles. Now, here, on the other hand, I have an equation. So the first thing I want to do, I want to solve this equation. I want to check that the Boltzmann distribution is a solution of this equation. Now, so let's try, let's check. So is a solution. Okay. Well, the left-hand side is very easy. There's no time. Left-hand side is 0. Now, the right-hand side must be 0. Well, there's a very simple way to show that the right-hand side is 0. Well, of course, if you plug it in and you crank and you evaluate up to second derivatives, you can convince yourself very simply. But I want to, refresh a concept that we discussed last time, that the Fokker-Planck equation can be written as a continuity equation where the current is defined this way. And it's a current in configuration space. So this is a 3n dimensional vector. Now, if I plug here, instead of P of equals T, I plug P naught, then you immediately see that the current is 0. Up to some diffusion coefficients, so I have to divide by D and beta. Yeah. And it's clearly 0. So this is telling us something. The equilibrium distribution is the stationary solution. Is the stationary solution of the Fokker-Planck equation. So Gibbs function distribution P naught equal minus u of x with a constant is the stationary solution of the Fokker-Planck equation. Now, it turns out that this is also, it's very, let me not go very deep into mathematics to show something extremely trivial. So let me use a little bit of mathematics and a little bit of physical intuition to sort of skip 2 lectures of mathematical details and go straight to the point. This is also the ground state of the Fokker-Planck Hamiltonian. So I can rewrite this as mh Fokker-Planck on P, and I can, now this is a way to write the Fokker-Planck equation. We all agree, right? Which HFP is, of course, negative d w square beta grad u grad Laplacian of u, right? Now, we already discussed that this is not Hermitian. And I was asking you to prove it, right? As a homework, right? Am I correct? I'm going to go over it in a moment. But the fact that it's not Hermitian implies that the right eigenstates and the left eigenstates, or if you want, the right eigenstates of the Hermitian conjugate, are not the same. So let me call it left and right. Now this is in general. Now the fact in general you don't have even a spectrum, you don't have a complete spectrum, and of course you have, if you have it, you have different left and right eigenvalues. And in principle you have complex eigenvalues, and in principle they are not the same. We shall show in a minute that the left and right have the same eigenvalues, but they're not the same functions. So wait a minute for the proof. Now, the statement that I want to make is that the Gibbs function is actually a solution of this equation, is the zero mode. That's the statement we just proven. And the very, very, very trivial statements is that it's the ground state. There's no, so basically the spectrum is bound from below. Well, how do I know that? Because if it wasn't bound from below, there would be no the system would continue evolving time to go to some lower states, but that wouldn't be a stationary solution. So basically, there is only one thermal equilibrium. That's all we are saying. I mean, I'm admittedly sloppy here. To do things very properly, you have quite a bunch of theorems to prove, to make sure that all these sorts of is completely rigorous from a mathematical point of view. It can be done. It's not a big piece of work, but if I do this, I don't do statistical field theory. And I think it's more important that we all agree that there is one thermal equilibrium. We are happy enough to the fact that it's a Gibbs distribution, and we move on. In a minute, you'll see a confirmation of this fact. So I just want to add one thing. I call this the Gibbs distribution rather than the Boltzmann distribution. And in my mind, the Gibbs distribution is the distribution in configuration space, because there's no momentum in the overdamped Langevin equation, while I will call the Boltzmann distribution the configuration, the Hamiltonian in phase space. Okay? And you can show that if you write the full Fokker-Planck equation in the underdamped limit, the stationary solution is still the Boltzmann distribution this time with a phase space Hamiltonian. So in other words, what we are discussing, the fact that the Fokker-Planck equation describes thermalization. And this is ultimately a consequence of the fact that we have derived the fluctuation dissipation theorem. And in fact, if you keep yourself, you can do the same derivation and then be more general. Do not impose fluctuation dissipation, and say do not impose that D is KT over M gamma. Okay, sorry, in your notes. Forgive me. Guys, pay attention. I wrote something, of course, wrong here. D is KT over gamma. So put a -1 there. Just realize that I wrote something incorrect. Okay? So if I have not used that, then my Fokker-Planck equation would have had terms, the coefficients here would have been different, right? Maybe you would have a C1 and a C1 here, and a C2 here, and a C3 here. Well, if you do that, then of course the Boltzmann distribution is no longer in general a solution of this equation, because the cancellations that lead to 0 to the right-hand side don't occur anymore. So the fluctuation dissipation theorem establishes that precisely the relative weight of these terms, and these relative weights of these terms are defined in such a way that they guarantee that you achieve thermalization. And which ultimately means that the Hamiltonian dynamics we have used to define the effective stochastic dynamics was consistent with thermalization in the limit in which the environment is infinitely large, which is exactly the concept of reservoir. So this, I mean, to me at least, I regard this as a fundamental result of statistical mechanics, because the entire building of statistical mechanics was relying on the fact that Hamiltonian dynamics was leading to thermalization. But at the same time, some of you may know that there's this thing called the return theorem. Have you heard about that? In Liouvillean dynamics. So this is a paradox. So guys, let's stop here for a moment, the lecture, and talk physics for a moment, okay? So whatever I'm going to say now, don't worry, don't bother writing down. Just bear with me in thinking, okay? So you might remember from your education in statistical mechanics the Liouville's equation. Now, the Liouville's equation is basically has the same structure of a Fokker-Planck equation, but it's in phase space, and it's the consequence of Hamiltonian dynamics, microcanonical Hamiltonian dynamics in a closed system, right? Now, the Liouville's equation conserves the volume in phase space, which basically says that if I have a set of states defined on a finite volume or configuration space, d gamma, and I let the system evolve according to the Hamiltonian dynamics, because of the specific properties of the Hamiltonian dynamics, that is Newtonian dynamics, meaning that the trajectories do not intersect, they conserve, and blah 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 blah, then this configuration will be evolving to a new volume in phase space, maybe this one, but this volume will have the new points will occupy the same volume as the original point. This is the notion of incompressibility of the flow of the Hamiltonian flow, of the Liouvillean flow. You must have heard this at least in your previous education, have you? Now, this fact has a tremendous implication, which puzzled mathematicians for a very long time. And it's the following. Because of this fact, if your volume is finite in phase space, if you start from a place and you let it evolve, ultimately you can always define a subset of it which will return to the same place. I mean, it's a theorem, it's not completely trivial, but basically, this will propagate around. And if you're in a closed phase space region, your initial state will return, your points will return to the same. At least you can always define a subpart of your initial distribution that will return exactly to the same volume, which is completely counterintuitive in terms of thermalization. It means that, you throw your dice or you start your system, you expect your system to be irreversible, never to come back. But what this theorem tells you, eventually, if you wait long enough, you come back to the same initial configuration. Or at least you can define a subpart that will come back to the same initial configuration. And this is very, now, mathematicians were puzzled by this because it contradicts the very notion of thermalization. Okay? Do you follow me, guys? Now, what this description tells you is that you can define very rigorously. Well, they went along with him by saying, well, the return is after all something that takes place in an infinite time, maybe 20 times the age of the universe or so. I never have to worry about that. And in fact, you can estimate that for the very simple system, the return would be like gazillions of years for any time scales you can think of. So basically, there's a finite probability, but it's small, so small that it's like saying, by tunneling effect, I can lean back to the wall and end up on the other side of the wall, but I never do quantum tunneling across the wall of my house and fall down on the street. Not in a 100 million times the age of the universe. So from practical point of view, this was never an issue. However, what the Langevin equation says is that if you, instead of trying to formulate the problem entirely microcanonically, isolating the system from the rest of the world, and you try to introduce the coupling with an infinite system, then you don't have this problem because your dynamics is no longer Liouvillean, it is stochastic, and you can show that you must equilibrate to the Boltzmann distribution. Now, then you play with the equivalence of the ensembles and blah, blah, blah. I find this kind of fundamentally irrelevant because it sort of compensates from a major sort of in statistical mechanics, you do sweep the dart under the carpet if you want. Okay. So now let's go back to what we ended last lecture with and discuss the spectrum. Of the Fokker-Planck equation. Now, the first thing I want to say, the Fokker-Planck operator is not Hermitian, right? What does that mean? Yeah, I can define an inner product between two functions, J, O, and H. And maybe this is the integral dx G. In quantum mechanics, you have a complex here, but we are in statistical mechanics. There's no point to use the same inner product that you would use in quantum mechanics because you have no phase. Let's define an inner product completely real. It's a perfectly defined inner product, right? Now, I can define another operator such that, let me call it O dagger, which is the adjoint of O, which is in general different from O. And I define in such a way to be the operator such that this inner product is equal to this inner product. That's the notion of Hermitian conjugate. You should be familiar with this. I apologize for repeating things, but last time I was telling this, some kind of uncertainty was in the audience, and the fundamental induction theorem for lecturing is if somebody is not quite clear-minded about, if there is a student who's not clear-minded about one topic, there are certainly n+1 students who have the same problem. And if you propagate that, nobody has an understanding of anything, which is not probably true, but you understand what I mean. So let me be pedantic here. So O is said to be Hermitian if it is self-adjoint. I'm not sure if the mathematicians are completely happy with this. I think so, but I haven't checked. But that's certainly the definition that physicists use. Okay, you've done this in mathematical methods for physics, I guess. Now, which means that O is Hermitian, is O is the same as O dagger. Well, let's check. Example of Hermitian operator, the Hamiltonian in quantum mechanics. Well, how do I know? Let me check. Suppose I have a function f. Suppose I have h of g. Well, I have d of x, f of x, g plus vx of g, right? Now, still in the realm of being pedantic, I define my Hilbert space as a space of integrable functions, meaning that the integral is never divergent. That means that the function is zero at the border or at infinity. So I can perform part integration without worrying about the boundary terms. Now, if you do part integration twice, the first term becomes negative sum of x times g. And of course, the second term doesn't even need part integration because I multiply by potential that is a scalar, and I can always write this potential as v of x f times g. Why not? It's multiplicative. So if I combine this together, I have that this is basically but this is nothing but the Hamiltonian applied to f and g, which means that basically h is self-adjoint. Okay? No big deal here, come on. Now, you immediately see where the problem stands when I do the Fokker-Planck equation. Now, let's go back to the Fokker-Planck equation. The Fokker-Planck equation contains a Laplacian. We just showed that the Laplacian is harmless. Contains the Laplacian of potential, which is a multiplicative factor, which is again harmless, because I can call this V and be happy with it. However, it also contains the terms which contains one derivative. And the fact that it contains a one derivative makes this not Hermitian, because all you need to do now is to take if you want to convince yourself, just look at the derivative, the gradient operator. Is it Hermitian? Obviously not, because this is still, again, if the Hilbert space is good enough, integral function, this is the negative of the gradient of f times g. So this is negative gradient of f g. So the adjoint of the gradient is the negative of the gradient. Is now everyone on the same pacing on this? So clearly, and that's why in quantum mechanics, the momentum has an I, if you think about it. The momentum operator is negative I graph, because given the structure of the Hilbert space, which has complex conjugation, when you apply, when you go on the left-hand side, the I helps you and saves the day. And in order to have observable quantities, you must have emission operators, right? Now, in stochastic dynamics, there's no such an I, and the Hamiltonian is not emission. And it's not emission for good reasons, because the hermiticity is associated with time invariance. Because if I take the Schrödinger equation, and I take the complex conjugate of the Schrödinger equation, I end up basically with the adjoint equation, but the hermiticity saves the day, essentially. Because it's basically telling you that the dynamics forwards and backwards in times in quantum mechanics is the same. But here we are in the realm of irreversible processes. And the dynamics that let me evolve forward in time is different from the dynamics that goes backward in time. However, and this is now in general, non-emission operators are bad guys. What do I mean? Well, they don't have a complete set of eigenstates to begin with. And if they have some eigenstates, they're not necessarily orthogonal. And if they are orthogonal, but the eigenvalue is not even necessarily real. So it's very difficult to work with non-emission operators because you can do very little with it. You cannot expand the function. You cannot do spectral representations. You do basically nothing. There's no spectral theorem. However, the Fokker-Planck operator is a very lucky non-emission operator. It's not just any non-emission operator, it's a privileged non-emission operator because it can be transformed into an emission operator by means of a non-unitary transformation. So what do I mean? I have my Fokker-Planck equation. And what I do formally, well, you can think about this in several ways, but one thing is to say, okay, the most intuitive perhaps is, let me define another function psi. And then
Professor,
yes?
Can I interrupt you for a moment?
Sure.
I have a question. I hope
Very good.
to formulate it well.
If you have problem with English, you can reformulate it after in Italian. But first try with English.
Okay. The fact that the Fokker-Planck Hamiltonian is not Hermitian and
Yes.
breaks time invariance as a consequence.
Yeah.
Is this connected to the previous interpretation of not having incompressibility and therefore not being able to return to the same phase space volume?
No. Yes and no. It has to do with no. I mean, from the physics point of view, of course, the Fokker-Planck equation is not incompressible. Doesn't generate a Hamiltonian, a Liouvillean type of incompressible fluid flowing phase space. There's no phase space for the Fokker-Planck equation in the overdamped limit, but if you were to do the underdamped limit, you would have the same problem. Okay, still is non-emission and blah, blah. So in some sense, it's more general than the Liouvillean equation. So yeah, there's no return theorem, but the return paradox is part of the thing here. The real thing is the Fokker-Planck, the non-hermiticity of the Fokker-Planck equation is important for irreversibility. Because there's only one direction of thermalization, basically. Like if when you solve classical mechanics problem, right? And you solve Newton's equation, and for instance, you have a pendulum, and you at some point you find a pendulum, and you get a position at time t of the position, and then you always have solution which you have to discard physically. Say, okay, this part is non-relevant because it's the part that led me here in the past. Remember when you were doing this exercise, right? You have always this part, this um, that has to do with the time in the past arriving to the point where I am, and this is not a physically relevant solution. I look at the forward time solution, something like that. Okay. There's no such an ambiguity here because remember Newton's equation is second order in time. So you can do t go into minus t and be happy with it. So the non-emisticity is ultimately related, as I will show you, to thermalization and to irreversibility, not so much to non-return, because there's no connection between Fokker-Planck and Liouvillean. I have no way to say what happens between these two. You see what I mean? It's not that you take the Fokker-Planck equation, you take a limit and you get a Liouvillean equation. It doesn't work that way. So I cannot tell you what is the extra ingredient of the Fokker-Planck equation that is responsible for this. Okay. I'm not sure I answered, but it's difficult to answer. I might think of a better answer in the future.
I think you did actually. Okay.
Okay, so let's go back to this.
Thank you.
Thank you for the question. So let's do this change of variable. Then of course I get dt. I get e to the negative beta half u dt of psi. And now, of course, you can crank the numbers here. But let me assure you that after you crank the numbers, well, we already basically done this calculation where we were doing the Fokker-Planck, where we were deriving Fokker-Planck from the path integral representation, going into the quantum mechanical and exploiting the fact that the Feynman propagator in imaginary time was obeying the Schrödinger equation. So you will not be surprised that this is the effective Hamiltonian times psi, where the effective Hamiltonian is negative d Laplacian plus the effective potential, and the effective potential was this famous d over 4 kt squared gradient square of u negative 2 kt Laplacian of u. Okay, now I can do basically the same game that I did when I was deriving the Fokker-Planck equation. I can multiply on the right by e to the beta. So let me say okay. So this is all being multiplied on the right. And basically what you can do is, throw this in and recover. No, sorry. Hold on a second. Sorry. I did something wrong here. Hold on a second, sorry. So this is e to the negative beta u. There's a negative here. There's h effective on psi. Okay, sorry. Now, what you can do, the next step was the wrong one. You can actually do the following. H, stick a positive and a negative. You're doing nothing, right? Here, because this is 1. So what you have is negative dt of e to the beta half u psi is equal to one operator, which is u h effective e beta u, times e to the beta half u psi. So you can rewrite this as a Fokker-Planck equation again. So I've gone back and forth to the Fokker-Planck equation. Oh, man. But basically, what I've done here is to show you that the Fokker-Planck equation operator, Fokker-Planck operator, can be written as in this form in terms of the effective Hamiltonian. Okay? Now, I like this form because it's basically showing that there exists a non-unitary operator. Let me call it, well, normally operators are called U, but that's because you assume they are unitary operators. So let me call O given by multiplied by the Boltzmann factor. And if I apply this to my operator and I transform the Fokker-Planck operator according to the standard laws of according to this law, I will turn the Fokker-Planck equation into an Hermitian form. So basically, it is possible to transform the Fokker-Planck equation to an Hermitian equation by means of non-unitary transformation. But you see, this fact has profound implication. The fact that you can write the Schrödinger equation, the Fokker-Planck, the solution of a Fokker-Planck equation in terms of solution of an Hermitian Schrödinger equation. Now you know that this guy has a complete set of states. And you know that the corresponding spectrum is real. So one thing you know is there exists a set of states such that this is obeyed and this is real and these are orthogonal. Right? Because the spectral theorem now applies to the effective Hamiltonian. Do you follow me? So the fact that the spectral theorem applies to the Hamiltonian allows me to construct a complete set of, no, I still have to define what I mean by complete, but I mean is a set of right eigenstates of the Fokker-Planck equation. This will be negative to the left u psi n. And if I apply the Fokker-Planck operator here, then I will get lambda n, right n, where these lambda are the same as this lambda. So the fact that there exists a non-unitary transformation that puts the Fokker-Planck equation into an Hermitian form is the special property of this Fokker-Planck equation, the Fokker-Planck operator. That makes this non-unitary, non-Hermitian operator a very lucky non-Hermitian operator, which does have infinitely many eigenstates. They are all with real eigenvalues. Not only that, it takes a little thinking, but I think you can convince that you can do the same and look at the adjoint of the Fokker-Planck operator. Let's call L of n. And how do I get the eigenstates of the adjoint? Well, the adjoint is basically the same Fokker-Planck operator with the negative signs in the gradient, right? Where is it? Here. Because this is Hermitian and this is Hermitian. Now, how do I get the eigenstates of the adjoint? Well, you do the same game, right? You transform this into an Hermitian form, and then you solve the Schrodinger equation and go back. And for the very same reason, you discover that LF of n is e to the plus beta half u of x psi. And guess what? Then it's immediate to show that the adjoint operator has the same spectrum as the real operator, as the forward operator. Ultimately, this has to do with the conservation of probability, as we shall see when we go into stochastic matrices. This is not a lucky coincidence. These properties follow from what is known to be left stochasticity. But this is just a name that means nothing to you at this level. It will become more clear when we will derive the Fokker-Planck equation or connect the Fokker-Planck equation to a master equation in a discrete set of states. But I'm just saying that the fact that we have this nice symmetry in the spectrum, we do have eigenvalues left and right, and they have the same eigenvalues. This is physically related to the fact that there is a conservation of probability. In other words, that the Fokker-Planck equation is not a Hermitian, but conserves the, but it still can be written as a continuity equation. Okay? Now, clearly, if I can show this, then my Hamiltonian is positive definitely as a potential, then clearly I've got the zero mode, that's going to be the ground state. So that's what I meant before. Wait a minute, and you'll be convinced that this is always the case. Now, observation. From the fact that left and right are related, by this transformation, it follows the following relationship between, what is this?
I guess the scalar product between the sides.
Yep, so let's try. Correct? I just applied the definition. So who tells me what this is? What is this integral?
Lambda squared.
Lambda squared.
No.
Okay, this is an integral, right? So it's an integral. I can cancel this out, right?
Yes.
Okay. And these are eigenfunction of the Hamiltonian, real eigenfunction because the Hamiltonian is real, but who cares? But now this eigenfunction of an emission operator, what is this? What is this?
Kronecker delta.
Kronecker
Vabbè.
delta, because it's these are eigenstates of an operator. They must be orthogonal. Yes, guys? Quantum mechanics 101. Okay, eigenstates of a Hamiltonian are form a complete orthonormal set of the Hilbert space. Basis set of the Hilbert space. So what we discovered that not only there are left and right eigenstates, they are a complete set and they are orthogonal, not in the sense of their Hermitian counterpart. So it is not true that Rn is delta, as you would imagine in quantum mechanics. This is not true, nor is for left, of course. However, there is some form of orthogonality linking right and left eigenstates. And this relationship here, I mean, guys, are you all with me in terms of mathematics here? Guys, I mean, it shouldn't be harder than, say, a standard advanced quantum mechanical course, right? Or even basic quantum mechanical course. So if you're not familiar with these concepts, please let me know. We have a problem. And I guess you will have a problem if you try to follow Fanzo's course. Okay, more than I. Okay. Now, these properties enable us to understand thermalization better by doing spectral representation of the Green's functions of the Fokker-Planck operator. In fact, so we are interested in the probability to find a system at position x given the fact that it was in t at x naught at time 0. Okay, fine. We have several times discussed the fact that I can write this in the following form. This is the effective Hamiltonian. Now, of course, I can stick in the resolution of the identity. Now, Federica, this is for Federica. Federica once asked me about this resolution of the identity in a discussion we had, like, come si chiamano I ricevimenti? And at the time, I didn't quite remember. She was a mathematician, so I sort of didn't sleep on that. When you do this, just remember this is a dual operator. It's not a complex conjugate of a vector. It's a projection operator that, it looks like it's a complex conjugate, but it's not a complex conjugate. It's a dual operator, right? The bra. I mean, I guess this is clear for all the physicists because they get exposed to that over and over and over. So I can write this in the following form. And this is X. I get my nice HT. And now here I get the eigenstates of the Hamiltonian. Okay? Now this is the wave function of the nth state in X naught. Now this is actually X n e to the negative lambda n t, right? Because this is an eigenstate of H. Now this would be actually, this would be the complex conjugate, but these are real Hamiltonians, so everything is real. There's no complex conjugations if you have a real Hamiltonian. You can always find a basis in a phase rotation that makes everything real. And basically, my propagator is written now as sum over n. And now, by recombining left and right from these two weights, this will go to this, and this will go to this. You will write that this is the sum over right eigenstates of X, left eigenstate of X naught, times the corresponding. And what this is telling me is that if I wait long enough, this is going to be R naught of X plus times L naught plus. This would be e to the negative lambda naught of t, but this is equal to what? What is the ground state of the Fokker-Planck operator? Guys, we discussed that. There's a
It's
station.
zero.
Zero. Okay. Plus R1 of X, left 1 of X, e to the negative 1 of t, plus so on, so forth. Finally, R naught is 1 over z. Well, that's the way of defining this. Left naught must be simply 1. How do I know? Because I know that integral dx left naught R naught must be equal to 1. And z is the partition function. That's the correct normalization. Okay? So what am I discovering? I'm discovering that the probability to be in X at T naught is precisely the Boltzmann distribution plus corrections. And the corrections are in principle unknown functions. But this expression enables me to understand what is the physical meaning of the spectrum of eigenvalues of the Fokker-Planck operation. In particular, the first non-vanishing mode, lambda 1, is the relevant time scales that tells me how long it takes to reach the Boltzmann distribution, because equilibration takes a time t, right? So lambda 1 gives me the characteristic scale that takes a system to equilibrate. So if I can diagonalize the Fokker-Planck operator, I have access to all the relevant timescales in my systems. Larger eigenvalues tell me about fast equilibration processes that become irrelevant. Let me give you an example. Suppose I have an energy landscape that is rugged, has many minima, but minima of different height. Now, how do I expect the minimum, the spectrum to look like? Well, if my temp, of course, it will depend on the temperature because the equilibration time scales depend on the temperature. Now, if my temperature is, say, barely smaller than the Earth, or saying kind of the order of these small barriers, and suppose there is only small barriers for simplicity here, if that's my temperature, and for sake of simplicity, let me lower this barrier here, otherwise it becomes complicated. Then I expect that I have a very fast equilibration in each of these states, and then a slightly slower equilibration in this basin, because crossing a barrier because of thermal fluctuation, if the barrier is just slightly after of KT, only requires a tiny fluctuation. But then I have a very, very slow process to cross this barrier. Because I need a lot of fluctuation to get here. So in general, my spectrum will look with a bunch of fast relaxation mode, which corresponds to local relaxation mode in each of these wells combined in some nonlinear way, But what I'm trying to say, this dynamics, the eigenmodes, this corresponds to fast equilibration. Then I have 0 down here, which is the ground state. And then I expect a gap and a small eigenvalue, because 1 over lambda 1 must be a large number. So the system equilibrates fast in a region here and waits for a long time to equilibrate globally. Do you see this physically? So you see, there's a huge amount of highly valuable information in the concept that we introduced. We understand how equilibration works. Now, it occurs on multiple timescales. Equilibration is not just something that has only one timescale in it. It has some timescales for fast local equilibration. And this goes back to our initial double well example, where we said, if I look at my initial distribution, I would imagine that after some short time, this will sort of go to a local Gibbs distribution on the left. Because if I wait too short for a typical time for a fluctuation that brings me here, I will not even know there is a right-hand state here. It's like being in Europe before Columbus. It took us several years, without hundreds of years of civilization before we fluctuated into the other side of the ocean. And until that time, we didn't know America was there, right? For the very same reason, these Brownian particles don't even know there is a right-hand side. So on a short time scale, they locally equilibrate on the left valley. But on a longer time scale, they begin realizing there is something beyond the ocean. And when equilibration occurs, so at the beginning you have a current flow, J, because there's nothing on the right, and some particle begin to go on the right. But if you wait long enough, then you build up a probability population here, maybe smaller than the one on the right, on the left, but still finite. And occasionally you have particles that begin to go back. So this compensates that the overall current eventually dies out. How do I know? because I know that if I evaluate the current of a stationary distribution is 0. So there is no flow in equilibrium. Well, you know, the situation is you're an astronaut. Here is space. You're in an isolated chamber. Here is vacuum. Now, your friend here outside of your chamber is angry with you, and he presses the button that you see in every sci-fi movie that opens the gate, and the air flows. That's the current. That's exactly the current. The air is subject to Brownian motion. But since this is no longer in equilibrium configuration, because it's like having, you know, a system with only one well and an initial distribution all on the left. This is not an equilibrium distribution. The system will evolve to the Boltzmann distribution, which will ultimately correspond to generating a flat distribution here over the entire system, which will generate a current. And that's why you see this. If you look at Alien, have you seen the movie Alien? It's of my generation, not yours, but it's a movie the way she kills the beast is by opening the gate of space, and this will generate a flow of air. And that's the same way that Spider-Man kills one of the nasty guys in the first movie of the Avenger Endgame, if I remember well, or whatever is that guy called, Infinity War. Right? So that's the Fokker-Planck current, nothing more, nothing less. Okay, the last thing I want to tell you today in 3 minutes is that I told you that the rate of equilibration across a single barrier is small. Sorry, is a small number, because 1 over lambda 1 must be large, right? Can I be a little bit more quantitative? Yes, there's a formula that allows you to compute that in some limit. It's called the Kramer's equation. We might go into that next time. But I just want to give you the physics of it here. Now I'm going to build a stupid model. So anytime you interact with the environment, you exchange energy, right? Anytime you get a kick from the environment, how much energy do you get per degree of freedom? KT, roughly speaking, right? That's half KT, fine. Let's say KT. We're not after the details here, okay? Now, let's assume that anytime you get a kick from the environment, you get it either from the left or on the right, okay? Because it's in 1D. And anytime I move by an amount that gives me a delta U of KT. Okay, delta U at each step is KT. It's a very crude model. How? So in order to cross a barrier U, I need to have delta U over, sorry, I need to have U over KT kicks all on the right. It's not really true. I could have 99 on the right and then maybe 3 on the left and then 4 more on the right. You see what I mean? So, I mean, I'm not trying to be exhaustive here. I'm just trying to give you a picture, right? So, but in this simple picture, in order for a barrier crossing event to happen, anytime I toss a coin and I decide I get a kick from the environment, I have 50% probability to be right or left. And in order to cross a barrier, I need this to be happening delta U over KT times, always on the same direction. So it basically is like tossing a coin for a very large number of times and getting all heads straight if I need to cross the barrier. Which immediately tells me that the probability to cross the barrier, or the rate, frequency to cross the barrier, is proportional to 2, in this very simple model, to the barrier height divided by KT. is exponentially small in the barrier height. Now, if you do things properly, as we shall do next time, you'll discover that there's a prefactor here, and this is not really 2, is actually E. And that's the rate of transition. We'll do it next time. This is the Arrhenius part of the equation, and this is the Cramer's correction. Fine, we'll do it next time. What I'm trying to say is that the fact that it's rare is because this is what I mean. This is what I mean when I say that you need the rare fluctuations for this to happen. Okay? But the rare fluctuation connects to the structure of the Fokker-Planck equation and generates a gap in the spectrum. And the gap separates fast dynamics associated with local thermalization processes to slow collective dynamics associated to global thermalization processes. And this multitude of scales is obviously a paradise for renormalization group theory practitioners, because you can integrate the fast dynamics and you know, you immediately see if your structure, if your barrier has heights of multiple structures, say small, medium, and large, then my spectrum will reflect that. There will be like a bunch of very slow eigenstates, a bunch of medium eigenstates, and maybe then up and all the other eigenstates associated with local thermalizations there. So the spectrum of the Fokker-Planck equation reflects the underlying structure of the energy surface in a beautiful way. So by integrating out modes here by RG, we can hope to capture slower and slower dynamics without having to worry about fast thermalization dynamics. Just as much as you don't have to worry about fast dynamics in the Schrodinger equation if you only want the lowest ground states and few lowest energy states. Okay? So this will be part of the course, and this is how renormalization group theory and stochastic dynamics begin to talk to each other in this course. Path integral has already spoken. Okay, 3 minutes past the deadline. Thank you for your lecture. I will upload this and the previous one today. Okay? See you Tuesday. Ci vediamo. Buon fine settimana, ragazzi.
Buon fine settimana.
Arrivederci, grazie.
Arrivederci. Grazie.